Now, coming to the idea of bootstrapping. Now, just one point to note, this bootstrapping has nothing to do with the idea of bootstrapping which we have discussed in fixed income because the names are similar, right? So at that time, recollect that in our discussion on interest rates, when we start with the par yield curves, we take the par yield curves, we run it through a bootstrapping calculator, and we come to the zero rates or spot rates. So please note that only the name is the same. The concepts are entirely different. That bootstrapping, which we have studied in our interstate module, that is specific to deriving the spot rates oblique zero rates. This is something which we try to relate from a generation of random numbers perspective. So please keep a note of this and do not get confused on the examination. Now, bootstrapping is another technique which we can apply in order to generate random numbers. Now, there's one key difference between what we use as a part of Monte Carlo simulation and what we use for this bootstrapping technique. Now, as a part of this bootstrapping technique, we rely on actual historical data. We don't really bother about the true random numbers which we draw from a distribution. We don't bother about that, but we look at what was the actual historical data. So that is the main difference between the usual Monte Carlo simulation and the bootstrapping technique. So the bootstrapping technique will repeatedly draw data from historical data sets and replace the data. So you can imagine that this works on the idea of replacement. So you draw the numbers from your historical data, you use it, you again replace the number so that whenever you make the next draw, again those numbers are intact and you can again draw them if required. Now, the thing is, we are not really drawing from a certain distribution, right? So recollect when we did our discussion earlier. So for a Monte Carlo simulation, you can have like a U01 distribution. You can use a uniform distribution through which you are drawing those phi increments, right? But here, since we are not doing that, right, it may be thought that the observed historical data is, and we are sampling directly from some kind of an unknown distribution because we are not specifying the distribution here. So that's another difference. Now, two popular techniques which we study as a part of bootstraps. One is the IID or independent and identically distributed technique, and next is a circular block bootstrap or CBB for short. So let's try to understand what these techniques are. Now, starting with the IID technique or the independent and identically distributed bootstrap technique. So under this technique, samples are drawn one by one from our actual historical observed data. And again, remember, we work with replacement. So even if we draw one instance of data from the historical observed data, we again replace it back so that we can again draw it on the next draw or any of the subsequent draws as well. So let's understand the simple steps. Right? So imagine that we require simulation of sample size of 3 and our observed data has 10 observations. The IID bootstrap technique is going to generate observation indices by randomly sampling 3 times with replacement. And our set of values which are given to us are from 1 through to 10, so we can choose any of these. Now to keep it generic, let me call these data points as x1, x2 through to x9. Actually, this should be x10, isn't it? So please read this as x10. So x1 through to x10. Now, say the following other draws. So I just made up these 3 draws. So as a part of the IID engine, so let's say on the first simulation, I draw x2, x7, xn. And remember, even if we draw these things, these are again to be replaced back. So we replace it back. Then we have a second simulation, we have a third simulation. So you'll see there are a few overlaps which happen. These overlaps are possible, i.e. we are able to sample certain values again and again because we are replacing it back after each draw. And remember that IID kind of a technique which we apply as a part of Bootstrap. This is something which becomes valid whenever the observations are independent in nature. But many times you observe that in practical applications, there is certain dependency between the observations which we have. So in that case, this method should be used very, very carefully. Now, talking on the circular block bootstrap or CBB for short. Now, we can imagine that CBB technique is a slight enhancement over the IID technique. And why we say it's a step ahead? Because it allows us to handle observations which are not independent of each other. So under this technique, so if you remember in the IID, we are drawing a sample one by one. Now here we won't draw a sample one by one, but we are going to draw blocks of observations. under the CBB approach. So the CBB samples are blocks which we are going to pick up. And again, the idea of a replacement remains the same. So even if we draw a certain block of observations, that goes back so that our data set remains intact and we can again use it for drawing purpose if required. So again, let's use this to a simple example. I've kept it generic. So say 10 observations are available and they are sampled in blocks of size of 3. So let's say I have 10 blocks which I can construct in this way: x1, x2, x3, x2, x3, and so on. So you'll observe that there are two things which we observe, right? So the first 8 blocks which we can imagine are they can use, let's say, consecutive observations. And then the last couple of blocks we are going to have to wrap around. Why wrap around? Because then we have to go around, right? So that way, I mean, from after x10 we don't have anything. So we need to have an x1 again which comes in. So this is what we'll observe here. Now, the only thing to remember is, or a couple of things to take care is, the block size used should be large enough to reflect the dependence in data, because remember that the CBB technique can be used to handle observations which are not independent as well, right? So that way there can be dependence in those observations. So that way the block size should be defined in such a way that we are able to pick that dependence in the right manner. Also, we should exercise one care that the block should not become very, very big. Because if the block is very, very big, then naturally that will reduce the number of blocks which we can work on. And that is not something which we want. Uh, Generally, you'll observe that from modeling perspective, if the sample is of size n, the block size chosen is square root of n. Again, this is not a hard and fast rule, but this is something which you commonly find being used by industry participants.